Hello everyone, Active Learning here. Welcome back to another video. In this video, we are going to discuss convolutional neural networks and it's going to be in depth. Alright, so after this video, you're going to have a great understanding of convolutional neural networks. So let's get started. So this will be the layout of the video. First, we'll talk about how computers visualize images. And then we're going to talk about how we will approach image classification using MLP, multi-layered perceptrons. We discussed MLP in our previous videos. So if you aren't aware of what MLPs are, please check out my previous videos. And we're going to understand why we can't use MLP for image classification on its own, right? So then we'll talk about CNNs. Okay, and then lastly, we'll talk about colored images. So let's jump right into our video. So let's talk about how computers see images, right? Instead of feeding a raw image into our model, our computer actually sees an image as a matrix of numbers, right? So in this case, 0 will be black, right? And then 255 will be white. So computers see colors, grayscale colors, black and white colors from a range of 0 to 255. So 255 in this case is white. And uh, in our case, we have a 28 by 28 image. So that's our image, 28 by 28. So that would mean 784 pixels. And each pixel value is from 0 to 255. Okay. So let's talk about how MLPs would try to classify images, right? How do we approach this problem using MLPs? So this is our multi-layer neural network structure, right? Our MLP structure. So let's talk about how that would work. So first we have neurons stacked on top of each other for each hidden layer, right? These red ones are hidden layers. These blue ones or green ones, these are input layers and these are output layers. So in our hidden layer, we have neurons stacked on top of each other. And it's important, very important to note that MLP is only taking 1D vectors. So we can't feed MLP raw images, right? So we have to feed it 1 by n, a 1D vector, right? So let's talk about how that will work. So in this case, for our image, we'll flatten it into 1 by 28 times 28, right? So that's 784 pixels. It'll be 1 by 784. So that basically means we have row 1, row 2, row 3, all the way up to row 28, okay? So that's pretty intuitive. Now let's get a visual representation of how this will look. So let's say we have a 3 by 3 grid. This is 3 by 3. Let's see how we'll flatten this so that it's 1 by n, right? So this grid will be flattened to 1 by 9, right? Since we have 3 by 3, 3 times 3 is 9, it will be 1 by 9. And it will be row 1, and then row 2, and then row 3, right? It will be a vector, 1D vector, okay? Now, let's just randomly create a MLP with 2 hidden layers that contain 512 neurons each, and we apply ReLU activation function for each hidden layer, okay? So each hidden layer has 512 neurons. I know it only shows 4, but just imagine there's 512, okay? So for our output layer, since we're classifying digits, we need 10 output neurons, right? One for each digit. So it will start at 0 because we don't just classify 10. It will be 0, 1, 2, all the way to 7, 8, 9, okay? And so what would this mean, right? This means that our total parameters will have a very, very large number, right? Parameter is basically the weights that we're training, remember? If you saw my previous videos, you know that our our model learns to optimize the weights, right? So this means that our model has to optimize this many parameters or weights, and that's a pretty large number. So the computational complexity of this is going to be pretty complex, I guess you could say. And so let's see how we calculate that, right? So parameters after layer 1, we have 784 in our input layer since we input a 28 by 28 image, which will be flattened into 1 by 784, right? And then we have 512 hidden units or neurons in our first hidden layer. Remember we created that? And then we also have 512 biases, right? If you watch my video, you know that biases are added to our weighted sum, right? So we have 512 biases, and that will give us this number. And then same for second layer and third layer, we do these calculations, and then we sum them up. And then we get this very large number. So if our input image isn't 28 by 28, it's a lot bigger, right? If it's a 224 by 224, for example, then this number will be very, very big, right? It'll be in the millions. So that's a drawback for using MLPs for image classification. And another drawback is spatial feature loss, right? So normally when we see a square, maybe we're classifying squares, we'll see it as this. This is also a square. This is also a square. But a problem with MLP is that it'll flatten this, right? It'll flatten this into, um, for this, it'll be 1 by 16, right? It'll flatten this into 1 by 16 1D vectors. Then if our if our MLP is trying to classify a square, it's going to be pretty hard, right? So this might be easy, but if we have this, right, then our model is going to be pretty confused, right? These are pretty random, so our model is going to be really confused. So it's going to be hard since we are losing spatial feature loss since they're all 1D now, right? So the drawbacks for MLPs, too many parameters, which leads to insane computational complexity, and we also get spatial feature loss. So that's why MLPs aren't that great for image classification. It depends on the situation, but generally you will use convolutional neural networks, right? Along with MLPs, you will see at the end. All right, so let's talk about how we approach image classification with convolutional neural networks. So first, let's talk about the similarity and differences between MLP and CNN, right? So the architecture of MLPs and CNNs are both composed of layers of neurons stacked on top of each other. And CNNs have different structures. It's convolutional versus fully connected layers. We'll see what this means in our later on, okay? So don't worry about any of this if you don't understand yet. And for weight and biases, both have weight and biases that are initially randomly generated, right? And then later on, they're improved through back propagation. And the main difference is that the weights in MLPs are in vector form since we have to flatten it, whereas in convolutional layers, weights take the form of convolutional filters or kernels. So we'll see what this means and later on in the video. So don't worry about it. And hyperparameters, convolutional neural networks have some hyperparameters specific to them, and I will show you what those are. And training, both networks learn the same way. So that's the similarity, okay? So now let's look at the big picture, right? And this big picture generalizes pretty well for most deep learning problems that you can approach, right? So first, our input data. It can be images, videos, text, anything. And we pre-process the data to get it ready for our model, right? And this means color transformation, right? Turning our colored images to grayscale, for example, and then standardized images, okay? And then for feature extraction, we're basically finding distinguishable information from the image, right? And then finally, learn from the extracted features to predict and classify objects by using our machine learning model. So let's see the CNN architecture. You might be wondering, what am I looking at? This is so complex. I do not understand. That is completely fine because at the end of this video, you'll understand everything that is shown here. Okay? So let me walk this through. First, we have input, right? So for our input, this is a 28 by 28 image, okay? And then we go through convolutional layers, conv1, convolutional. And I'll explain what kernel and paddings are. And also, all of these I'll explain, so don't worry. And we get something like this. So what is this? This is something called feature maps, right? Feature maps are basically the output of one filter applied to the previous layer. So we applied convolutional here to our input, and then we get this feature map. So I'm just giving you some definitions, and I will explain what each of these are later on. So this is just a general overview, you can say. And it is called a feature map because it basically maps out where certain features are found in the images, right? So it will map out important features. And then CNNs look for straight lines, edges, and objects. So it looks for key features in there. And whenever these features are spotted, it will basically be reported to the feature map here. And you can think of feature extraction step as breaking large images into smaller pieces of features and stacking them into vectors. That's basically how I understand them. Like you're cutting this two up into small pieces of features, right? And then we cut up even more later on, right? So that's pretty intuitive. And what do you notice here? Well, I noticed that the dimension reduces while the depth increases, right? So you see that this one's getting longer and longer while the dimension is reducing, right? 24 by 24 to 12 by 12 to 8 by 8 to 4 by 4, right? So that's an important observation. We'll explain. I will explain what this means later on. Okay. So first, let's start with how CNNs learn patterns, right? So first, in our first convolutional layer, for example, in our first layer, it'll learn something basic like random features, super basic features, and then the further along, we might get something that's recognizable, right? For example, we got eyes, the teeth, the nose, right? And then later on, the deeper we go, it might actually transform this into something that we can understand and recognize, right? These are human faces. So that means that CNNs don't learn all the features in one layer. And it typically happens over tens or hundreds of layers. The layers learn more and more complex features the deeper it is, right? That's what we're seeing here. Now, let's talk about the basic components of convolutional neural networks. And these three, you kind of have to know, they're pretty important. We have convolutional layer, basically the building blocks of convolutional neural networks. And we have pooling layer. This one's pretty important, but some people might argue that this is actually not needed. And in the future, we might actually see them being completely removed. But yeah, convolutional layer is really important. And then lastly we have fully connected layer. Let's just say FC for short, okay? Now let's see the typical convolutional neural network architecture. So for CNNs, rally activation function is used after convolutional layers. Now, we will dive into each of these components, so don't worry, but I'm just providing a typical CNN architecture so um, you can understand the basic component, where the basic components are located. So, first we have convolutional layer, right? And then it's typically followed by a pooling layer. And you'll understand why. I will definitely explain this. So typically convolutional layers are followed by pooling layer. Um, it could be two convolutional layers followed by one pooling layer. It could be one convolutional layer followed by pooling layer. And then after we do all this, we flatten it. And this is where our fully connected layers are, right? Remember that we have to flatten it so that it's 1 by n, so our MLPs can learn, right? And you might be wondering, why are we doing this, right? I thought we don't have to use MLPs. Well, later on in the video, I explain why we are using MLPs, right? And this part is all feature learning. We're learning the important features. And after we gather all the important features, we feed those important features that we recognize into our classification using MLP, right? And finally, we use softmax activation function and we get a probability for each digit, right? 5 seems to be the highest here. Okay. Um, yeah, that's about it for basic CNN architecture. I'll explain what every one of these terms you see on the screen means. Okay, so let's first start with convolutional layer, right? Convolutional layers are the core building blocks of CNNs, and you can kind of think of convolutional layers like a sliding feature window that slides over the image pixel by pixel to extract meaningful features, right? And this is like our sliding window. We're sliding over pixel by pixel, and then we're extracting the meaningful features. So how this works is actually matrix dot product, right? We're multiplying 0 by 9, and we add that to 2 times 4, and we add that to 1 times 1, and we add that to 4 times 1, right? And then we get the sum, which is 16, right? And this 3 by 3 kernel that you see in the middle is actually called a kernel. And basically the kernel slides over the original image and does some math operation, matrix dot product, right? To get the value of the new image on the next layer. Or you can say convolved image, okay? And the area of the image the kernel convolves is called the receptive field. Yeah, this is kernel and this is the receptive field, okay? Now, for CNNs, you can think of kernels as weights, right? Just like MLPs. These, you can think of weights that our model tries to adjust every time through back propagation. So you can think of these as weights. And, same thing as weights for MLPs. They're randomly assigned initially and they are improved through back propagations, right? Okay, now we can see how math is really similar as well. This is basically the weighted sum, right? Same as MLPs. We're taking the weighted sum and then we add in bias, right? So this is really similar with MLPs, except we are keeping our spatial feature, right? So we don't lose spatial importance. Okay, so this is all pretty intuitive, right? If you don't really understand, it might be because you haven't watched my previous videos, so please check them out if you haven't already. And okay, so lastly, this convolved image, it's called the feature map, okay? So the kernels basically filter out unnecessary information and amplify features in an image, okay? this is called the feature map, where all the features are, right? We talked about this in our previous slides. Now, let's see how it actually works. So let's say we have an image. I stole this from online. We have an input image, and right here we have an edge detection kernel. Remember what kernels are? The 3x3 grid that we pass over our image. Okay, and it'll basically detect the edges, which are important features, and then our convolved image might look something like this, right? This is our feature map, right? Okay. Now let's see how we'll code this using TensorFlow. First, we have to import convolutional 2D. It's 2D here because we're working with two-dimensional images, right? 2D images. And filters equals 16 here means that we will have 16 kernels, right? That it basically represents the depth of the output, right? Remember the depth of the output, okay? And kernel size equal 2 here means that instead of a 3x3 kernel, we have a 2x2 kernel, okay? And you can think of it as a 2x2 sliding window. Now, I'll talk about what strides and paddings are, and pretty sure you guys know what relay activations are. Relay activation works best with convolutional neural networks, so it's important to know what they are. I might cover them in a future video. This one is really important, okay? So now you can think of convolutional layers like hidden layers, right? They're basically hidden layers for MLPs. And the kernels are the equivalent of the number of neurons or hidden units for MLPs, right? The kernels, and each kernel unit is considered a neuron, right? For example, if we have a 3x3 kernel, then that means we have 9 hidden units. And if we have 2 filters, which means 2 3x3 kernels, then we have 2 times 3x3. That gives us 18 hidden units, right? So by increasing the number of filters, we're making our model more complex, right? Just like adding more neurons for MLPs. So let's talk about strides and padding. Strides basically means the number of steps that our sliding window is moving over, or our kernel is moving over. So for example, this um, turquoise color, right? You can see that it first starts here, and our second one will be here. So our strides equal 1 in this case, since we're only moving over by 1, right? We're only moving over by 1. So this is what we get, right? And this output volume will be smaller if our strides is larger, for example, 2. And strides basically determines how long it will take to train your model. Larger strides would mean that your model takes less time to train, right? Now, padding basically is this perimeter of zeros around our original image, right? So padding is most commonly used to allow us to sort of preserve the spatial size of the input volume, so the input and output width are and height are the same. And this way we can use convolutional layers without necessarily shrinking the height and width of the volumes, right? Okay. Now let's talk about max pooling layers. So we saw how the convolutional layer increases the depth of the output layer based on the number of filters we set to, right? So this increases the number of parameters that our model needs to optimize, and that increases our computational complexity. So this is where max pooling layers come in, but we're specifically talking about max pooling layers here. So what max pooling layers are, basically they're basically sliding windows as well. They're kernel sliding windows, and we also provide them with a stride value. So in this case, the stride seems to be 2 since we're jumping over 2 values, right? and we're basically taking the largest largest value in um, every kernel that we slide over, right? And it's a common practice to add max pooling layers or pooling layers in general after convolutional layers to reduce the dimensionality, right? So this will give us a 2x2 image instead of a 4x4 image, right? And basically the goal of pooling is to downsample the feature maps produced by the convolutional layer into a smaller number of parameters, and which reduces computational complexity. Okay, now there are actually two types of pooling. One is max pooling and the other is average pooling. And we'll talk about what average pooling is, but we just talked about what max pooling is, sort of. We're basically taking the max value over here. And yeah, it's pretty intuitive. It's really easy to understand. And the hyperparameters for max pooling is only the kernel size and the stride value, right? So that's the only hyperparameters we have for max pooling. So if the convolutional layer has 3 feature maps, the output will also have 3 feature maps. I'll explain what I mean by this. So um, note that the depth will stay the same. So instead of 1.1, let's just say we have an image like this, right? The depth will actually stay the same. You notice how this is also 4x4. We get the max value here, and we actually reduce the width and height, but the depth stays the same. Okay, so that's important to know about pooling layers. And in summary, pooling layers basically help keep the important features and pass them to the next layer while shrinking the image dimensionality, right? This will reduce computational complexity, okay? Now let's talk about global average pooling. This is actually a very aggressive way of pooling, which calculates the average of the entire input, right? Uh, it calculates the average of the entire feature map. Okay, so it's just a more aggressive way of pooling, but typically you'll see max pooling layers. These ones are the most commonly used. Okay. So let's see how you actually code this in TensorFlow. It's really simple, right? It only requires 2 lines of code. So it's basically, we set the pool size, which is 2x2 in our case, and our strides is 2. You can set this to 1. It doesn't really matter. Well, it does matter, but you can do some experimenting. So I don't want you guys to freak out about hyperparameter tuning because typically it doesn't require that much work. You'll be using models created by other people through transfer learning, and you don't actually have to worry that much about hyperparameter tuning. It's just a lot of experimenting, okay? So let's visualize what that actually looks like, right? So we're adding convolutional layer, and then we apply pooling layers. So it might look something like this. Notice how the depth increases and our width and height also decreases, right? This is because of pooling layers, and convolutional layers basically um, produces this, right? Okay. Um, and then we might get a long tube like this for our feature maps. Alright, so now let's talk about fully connected layers. So why do we actually need fully connected layers? Right, so after going through pooling layers and convolutional layers, we have this extractive feature tube, and then we basically pass this to our MLP. But before we do that, we have to flatten this, right? Remember that MLPs only take one-dimensional vectors, so that's why we have to flatten this and then feed it through this. And in this case, it's 1 by 1000 since we have a 3D tube here. So 5 times 5 times 40, that gives us 1000. And in general, MLPs are actually great for classification, but not image classification, since they lose important features like we saw in previous video due to spatial loss, right? So that's why uh, once we have these important features too, we can flatten this and feed it to our MLP. So that will actually be better for classification. And notice that our output is between 0 and 9 since we're classifying digits, and we'll be using softmax. Softmax is the activation function you will see for multi-class classification. If you're doing binary classification, you might use sigmoid function, right? Okay, now let's talk about adding dropout layers to avoid overfitting. So what are dropout layers and what is overfitting? Okay, so overfitting basically means that our model is fitting too well on our training data and won't work well on new data. A dropout layer is one of the most common methods used to prevent overfitting, right? So we're basically deactivating some certain nodes here, right? We're deactivating certain nodes. And it basically allows us to deactivate random nodes every epoch, right? So this way we can prevent some neurons being stronger than others, right? We can deactivate this one, for example, and then next time we can deactivate this one. And the hyperparameter for dropout layer is the dropout rate. And so in our case, the dropout rate is 23% since we're turning off 23% of the neurons in our MLP, right? Okay, so yeah, this is the best method, well, the most popular method to reduce overfitting. Now let's talk about convolution for colored images, right? RGB, with red, blue, and green, you can create any color, right? Any color you want. You can create them with RGB, okay? Now, let's say that we have a colored image, and for each pixel, we will have a value for red, green, blue. Uh, these numbers indicate the intensity from 0 to 255, right? Okay, so the lower the value, the higher the intensity. Okay. Wait, actually, sorry. I think it's the other way around. Yeah. Okay, so um, this means that we'll actually have a 3D matrices, right? One for red, one matrix for red, one matrix for green, and one matrix for blue. So this will create a 3D matrix for this image, right? And if this is a 28 by 28 image, this isn't, but let's just say it is, then if it has color, it will actually be 28 by 28 by 3 since we have 3 matrices, one matrix for each color. So every matrix would be it will be a 2D matrix, right? So since we have 3 matrices, that would increase our time complexity, right? Instead of one matrix, now we have 3. That will greatly increase our time complexity. So a general tip is to determine whether if it is even important to have colors for your image classification, right? So if you're classifying certain images, it might be important to have colors. The colors might be important, right? But in other cases, if you're classifying like digits, it doesn't really matter whether the digit is written using a green pen or a red pen, right? We only care about what digit it represents. So in that case, we can actually turn it into a grayscale image, which means black and white image. So that will actually reduce the time complexity, okay? So that's something important that you have to keep in mind as a deep learning engineer or machine learning engineer, right? So let's summarize. In this video, we talked about how computers see images, grayscale images, and we talked about how we will approach image classification with MLP and why that doesn't work as well. And then we talked about CNNs in depth, right? We talked about every one of these. These ones are hyperparameters for CNNs, right? And then we talked about max pooling layers and why we need those. And we talked about dropout layers, right, to reduce overfitting. And then lastly, we talked about colored images, RGB, right? Okay. Yeah, that's it for this video. If you guys enjoyed this video, please leave a like and subscribe. And if you are still confused about something, please ask them down in the description below. Sorry, ask them down in the comments below, and I will answer them as soon as possible. And yeah, thank you guys for watching. See you guys next time.